Hey, this is Parul Gupta presenting her final assignment for Model 1 completion Machine Learning Foundations, part of AI Product Management course. Let me start off by giving the project context. So, we focused on building a predictive model to forecast the electrical energy output of a combined cycle power plant. Our model is driven by a dataset of 9,568 hourly records collected through sensors placed across the plant. These include key environmental factors such as temperature, pressure, humidity, and exhaust vacuum. Each of these influence the plant's performance. And the goal of this initiative is to use these parameters to accurately predict the net hourly energy output, ranging between 420 to nearly 496 megawatts. By doing so, we are trying to enhance forecasting accuracy, support better planning, and optimize overall plant operations. For our predictive modeling, we chose to leverage Google AutoML. That's a powerful tool that automates some model training and optimization. This allowed us to efficiently build a high performing regression model and derive deeper insights into the energy output patterns of the power plant. I explored different regression algorithms with optimization objectives such as RMSE and MAE to ensure both accuracy and interpretability of results. My model considered key ambient features, which is AR, AT, pressure, relative humidity, and exhaust vacuum, all of which have a significant influence on the energy output. And to maintain the model integrity and avoid overfitting, I followed a robust data split strategy: 80% for training, 10% for validation, and 10% for testing, enabling me to have reliable performance evaluation across the unseen data. For the model building process, I begin by uploading a cleaned data set in the Excel format to Google AutoML, given my goal to predict a continuous numerical output, which is net hourly electrical energy. And so I selected regression as the modeling objective. To streamline the development and tap the advanced optimization, I chose AutoML as the default training method. This allowed the platform itself to automatically evaluate multiple models, tune hyperparameters, and identify the best performing configuration based on the defined features and regression goals. In the second step of model, I selected PE, the net hourly electrical energy output, as the target column for production. For data partitioning, I opted for random split method, allowing the ML to automatically divide the dataset. As a result, it was split between 80 and 1010. This randomized distribution ensured a balanced and an unbiased sample across all subsets, which is very critical for building a generalizable and accurate predictive model. In the final step, ML presented a summary of the model configuration, including the selected dataset, the regression objective, the target column PE, and the data split method. At this stage, I confirmed RMSE, that is root mean squared error, as the default optimization objective. RMSE is particularly effective for this use case as it penalizes larger errors more heavily, helping me achieve a model that prioritizes precision in predicting energy output. To evaluate the accuracy and robustness of my predictive model, I considered three key performance metrics. All offered unique insights. RMSE, that is highly sensitive to large deviation, helped me in identifying and penalizing the significant prediction errors, which is critical when precision in energy output forecasting matters. Next, I used MAE, which treats large errors as outliers, making it ideal for datasets where I want a balanced view of overall performance without letting extreme values dominate. And finally, I included root mean square logarithmic error. This metric evaluates relative errors, making useful when actual and predictive values span a wide range. It was effective in this scenario because predictions must remain non-negative, and scale sensitivity is important in our. In the model prediction test, in conclusion, our predictive modeling initiative has provided strong evidence of how environmental factors, especially temperature, influences the energy output of the power plant. And so, using Model 4 optimized for mean absolute error, we conducted targeted trials and consistently found that AT has played the most critical role in driving the output. And in contrast, relative humidity showed a relative minor impact and can be deprioritized in future iterations. Most importantly, the model delivered a high R2 value, which is R square of 0.961, reflecting strong predictive accuracy and explanatory power. These findings not only validated my approach, but it also offered practical insights for improving operational efficiency and planning. So that concludes my final assessment for the first module I had covered in AI product management. I hope this turns out helpful to others who are watching this video. Please feel free to drop any comment should you have any. Thanks.